Hello Internet, welcome to another tutorial in Digital Electronics series. We'll discuss 2-bit comparator today. 2-bit comparator is a logic device used to compare 2-bit numbers. If we were to understand the functioning of a 2-bit comparator, it will be something like this. We have one number composed of 2 bits A1 and A2, and that number could collectively be known as A, and another number again of 2 bit is made up of B1 and B2. Collectively it is known as B. Now if we were to compare A with B, there can be three cases. The first case can be when A is greater than B, and we can get an output by the name of G. The second case can be the case where A is equivalent to B, and the third case is when A is less than B. So I create three inputs by the name of G, E and L, depending upon whether A is greater, equal or less than B. So if we were to make the truth table of a 2-bit comparator, it will essentially contain 4 inputs, but those 4 inputs are seen as 2 bits pairs. So in other words, if we were to fill up this truth table, and if we see the first case where number A is 0 0 and number B is also 0 0, so I'll fill up the case that it is this case where A is equivalent to B. So when we give 0 0 0 0 at the input, this output will show up as 1, because it is the case of two numbers being equal, and G and L will become 0. And that's how we need to fill this truth table. In the second case, A is 0 0 and B is 0 1. So which is the case when A is less than B. So I'll say A is less than B. So I'll put a 1 here and a 0 0 here. And similarly in this third case, it is again a case of A being smaller than B. Fourth case is also A is smaller than B. Now the fifth case where A is 0 1 and B is 0 0, of course A is greater than B, so I put a 1 here and 0 0 here, and the subsequent case is A and B are equal. Then we have two cases where A is smaller than B. And now in this case A is bigger than B. In this case also A is greater than B. And in this case they both are equal. And in this case B is greater than A, and in this case A is greater, A is greater, A is greater, and in this case A is equal to B. So that is how I fill this thing up. So I hope the logic behind the working of a 2-bit comparator is clear from the truth table. So these two inputs are seen separately, and these two inputs are seen separately. They are compared, and this truth table is made. From the truth table, we need to draw 3 K-maps, one for G, one for E, and one for L output. Now I already have inputted the values of ones in their appropriate boxes in the K maps for G, E and L. As you can see, for ones occurring in these boxes, we'll need to form three product terms so that all the ones are featured. So for G, for this one we get A1 B1 bar, plus for these two ones we get A1 A2 and B2 bar, and for these two ones we get A2 B1 bar B2 bar. For the value of E, we get this. You need to write the expressions for all these ones individually, like A1 bar, A2 bar, B1 bar, B2 bar as the first product term, then A1 bar, A2, B1 bar, B2 for the second, and then after writing the four product terms and simplifying, you'll get A1 XOR B1 multiplied by A2 XOR B2. And for L, the simplification will give us, let's solve this once in this box. So we have A1 bar and B1 plus for these two we have A1 bar, A2 bar and B2, and for these two we have A2 bar, B1, B2. So we have formulated the expressions for G, E and L. Now from these expressions we'll need to draw the circuit diagram. For circuit diagram, I've taken all the inputs A1, A2, B1, B2 and their complements using the NOT gates. The first input is A1 B1 bar. So I've taken A1 and B1 bar from here. So the second product term is A1 A2 and B2 bar. I'll multiply them using a NAND gate. Then I take A2 B1 bar and B2 bar, and summing all these product terms using an OR gate will give me G. Next we have A1 XORed with B1, and then A2 XORed with B2, and we need to multiply them because we have a dot here to get E. Then for L we will take we'll need to take A1 bar, then B1, A1 bar again, A2 bar, B2, and the last term is A2 bar, B1 and B2. and adding these three will give me L. So this black box of 2-bit comparator is a complex structure of gates which has all kinds of AND gates, OR gates and XOR gates. They are taking 4 inputs and generating 3 outputs like this. So I hope the logic behind the working of 2-bit comparator is clear, and I hope you liked the video. I'll post more videos on comparators. We'll discuss 4-bit comparators and 8-bit comparators and their rationales, their usages. And thank you so much for watching this video. You have a great day ahead. Bye.